So in this lecture we're going to be building up to the identity theorem, which says that if we've got an accumulation point where two functions agree, then actually they must be identically equal to each other. This relies on the fact that the set that we're considering is connected, so connectivity will come in to the picture. So before we get to that, let's first make some observations. The first one is that the set that we'll call O as the set of points such that f has a zero of order infinity is an open set. Okay, so having an order infinity will kind of be related to the identity theorem, right? So if we look at the Taylor series, right, we're considering obviously f is a holomorphic function, right? It's a holomorphic function, and then we define the idea of the order of a zero, right? So the order of a zero of f is defined to be the minimum of k such that the kth derivative at z0 is non-zero. So if it's order infinity, that means all the derivatives vanish. So this is an open set. Okay, so that's very important. Okay, so that means that, well, so what this basically means is that at z0 all the derivatives vanish, right? Okay, I'm getting a bit ahead of myself. So why is it true that this set is open? Okay, well, we look at the Taylor expansion, right? We have to look at the Taylor coefficients. So if f has a zero of infinite order at z0, then all the Taylor coefficients at z0 vanish. Okay, so alright, so basically if we use Taylor's theorem here, right, we have that basically that the Taylor series exists. Okay, so I want to be really careful, right? So f is holomorphic on a region D, right? That's our assumption. Okay, and so these are satisfied. Okay, and we've got a z0 in D and an r greater than 0 such that the closure of this sits inside D. So that means, so this is the important point, right? Suppose this region D is this kind of funny looking shape, right? So, okay, so just because f is holomorphic on D doesn't mean that the Taylor series given by this is going to converge everywhere, right? It doesn't mean that this is valid on all of D. What you have to do instead is you say, okay, this is the point Z, there's some point z0 in D, and then you fit a radius, and it's large enough, well, it's small enough that the entire disk, the closure of the disk, sits inside D. Then the Taylor series is valid only on this disk, right? So there's not necessarily a global Taylor series that is going to work, right? It's got to be, it kind of the shape of D matters, right? However, like I said, this Taylor series around the point z0 will be valid on a neighborhood. So that means that if f has a zero of order infinity, that means on some neighborhood of z0, the Taylor series of f exists, and then each of the coefficients, which are given by, the nth derivative at z0 divided by n factorial, they're all going to vanish. And so Taylor's theorem tells us that f would have to be 0 on this open neighborhood right here. Okay, so that's why O is an open set. Okay, but importantly, even though D is connected, it's not true that f is going to be identically 0 on the whole of D. It's just going to be identically 0 on an open set. Nevertheless, this guy is an open set. Okay, or it could be the empty set, but the empty set is open. Okay. Now what we're going to do is we're going to actually also show that this is a closed set as well, and then we'll get the identity theorem, right? So, okay, I said just a moment ago that it's not true that if f has a 0 of order infinity, the function is going to be 0 on the entirety of D, right? Actually, that does turn out to be the case, but we're going to have to make some further arguments to prove that. Okay, and that's where the connectivity of D will come in. Okay, so now for the next remark. All zeros of finite order are isolated. Okay, so suppose that f has a 0 of finite order, of order n less than infinity, at z0, then in a neighborhood of z0, but not necessarily on the entirety of D, on a neighborhood of z0, f of z can be written as the sum from k is equal to n to infinity of this. So basically the first derivatives are going to be all 0. Right? Because this is just by definition, right? A0 times the Taylor series is f of z0 plus f dash at z0 times z0 and so on and so forth. The first n of these guys are going to be 0. And so this actually tells us that in some neighborhood we can write f as g of z times z minus z0 to the power of n, where g is a holomorphic function that is not 0. And in fact, it doesn't have any zeros in a neighborhood of z0. Okay, right, okay. So in other words, all zeros of finite order are isolated. Finally, suppose that f has a 0 of infinite order at a point z0. Then f... Okay, so actually f must vanish on all of D. Why is that the case? Well, we said that the set O is open, right? But also it's closed as well, right? It's also closed in D. Why is that? Suppose that Zn in O is a sequence which converges to some Z in D. Well, that means that f of Zn are all 0, and that means that therefore f of Z must be equal to 0 by continuity. Okay? So that's where the continuity comes in. But Z cannot be a 0 of finite order because then it would have to be isolated. So that means that Z is also in O. Okay? So O is a subset of D that is open and connected, open and closed, and since D is connected, O must be the entirety of D. Or it's got to be empty, but it's not empty because F has a 0 of infinite order. Okay? Alright, then we're gonna, okay. So actually we've shown that the zeros of a holomorphic function are isolated. That's not technically completely true, but because if it's infinite order then it's not the case. However, when we talk about zeros of an analytic function, we very rarely mean a 0 of infinite order. So, henceforth when I say zeros, unless I otherwise state the possibility of having a 0 of infinite order, we just say that it's finite order. Okay? Cool. Now, we've got a very important consequence which leads to... Alright, okay. We have a very important consequence. Alright, fine, I'll finish this bit. Okay, so okay, I'm not sure if this is really necessary. So let me talk about the identity theorem, okay? So suppose that D is a region, okay? And we've got F1 and F2 going from D to C that is holomorphic, okay? Suppose that the set where the functions are equal has at least one point accumulation in D. Then that implies that F1 is equal to F2 on all of D. Okay? So the proof of this is that let's just take G to be F1 minus F2. Suppose that Z is a point accumulation okay. So I think of that set, okay? Yeah, so say that Z is a point of accumulation of the set Z in C such that F1 of Z is equal to F2 of Z, okay? Then that means that G is a holomorphic function because it's F1 minus F2, and it has a 0 in Z which is not isolated. Therefore, the 0 must be of infinite order and therefore vanish everywhere. And that's the proof of the identity theorem.